record. Sorry. So I'm going to repeat in 2 minutes. So we are designing the core, which is a mathematical tool that finds whirlpools at points. So that's the definition, and we have been explaining it. I am not going to go a lot further, but the crucial part just comes now. If you have a closed path, so you are swimming in a river, and the river has no forces that go around. Say the river has forces only in one direction without any rotation. Then if you start swimming against the current, you will have to spend some work. If you are swimming against the current, with the current, you will have a net, you will have a net gain. But if you go around from starting one point, swim and coming back in the same direction or some other direction, but in the end, the flux, the money integral or the work integral becomes zero. This automatically means that in that region, and it could be a point, we're going to shrink it to a point, automatically means that at that point, there are no whirlpools. And if you have a little whirlpool, it doesn't matter how big or small it is, then when you go around this, you will either gain or lose money. Let's say that you go this way and return that way. So you will gain or lose some money. Now, what if you go around that way and return the same way? So it's zero. So it means you're not really doing any work. But you are not describing a point. But the moment you move a little bit out of this way and you describe, let's say, what is happening at that point, you will see that the field is not the same in your way forward and in your way back. So automatically you have to say, oh, there is a whirlpool there. Because in none of the other fields, the work will be zero. Okay, so that is the fundamental thing. That if you have a closed path and inside that closed path, the work integral is zero, you don't have whirlpools. And if it is different from zero, you have a whirlpool. So that is, or an eddy, you can call it instead of a whirlpool, an eddy. Yeah. And I don't know how you would call it in different ways. All right. So therefore, we're going to do this. We're going to do the integral around this path that covers the point. Okay, and at some point, so we do the work integral here. So we're going to do the work integral of f of dl, just to determine if there is a whirlpool in that region. But then we're going to say when the area described by the this thing, in fact, it's the other area, but I don't want to put so many lines. But let's say this area, when the area described here, we tended to zero, which means basically it's not really the area by itself tending to zero. It means that in this case, delta x tends to zero and delta y tends to zero. So we shrink it to a point from both sides. We don't shrink it to a line. All right. So, and if we do this, first of all, we have to discount the area. And that's how is the informal derivation of the chord. So what we do is we're going to have 4 points. I'm going to put them in black. We're going to have 4 points in which we integrate. We integrate there, we integrate there, we integrate there, and we integrate there. Okay. And we are going to put the coordinates of these points, right? Let's say the coordinate of this point will be, let's call it a P of x plus delta x by 2. So it's moved from the plane, from the YZ plane is moved delta x by 2, being delta x, of course, the thickness of this rectangle or the height of the rectangle, the side of the rectangle. And that would be, comma, y delta y by 2, and at a point z. Now, this other point, let me actually see if I can change it to another color. Let me see. No. Let me see if what I can do. Let me put it here. No. Well, I'm going to leave it the way it is. Now, this other point, this will be easier. This point is x plus delta x by 2 is on the same side, on the same face on the xy plane. But now it's on the other side of the y, right? It's y delta y by 2, and it's still at z because it's on the upper side. And all of them is going to be on at z. This point is going to be x minus delta x by 2, and it's going to be y minus delta y by 2, and still z. And this final point will be at x minus delta x by 2, comma, y plus delta y by 2, comma, z. Okay, and now I do the integrals. Immediately there will be 4 integrals. So I have the first integral that is going to be from y delta y by 2 to y plus delta y by 2, and this is going to be fy dy minus, following the path, right? The integrals have a path. Is going to be y minus, no, y plus delta y by 2, y minus delta y by 2 of fy dy. It's the same thing with different limits. Plus the integral from x minus delta x by 2 to x plus delta x by 2, fy dy. I am going to complete, I can write it all, and then I am going to, and they will be negative, delta x by 2, and then I'm going to explain each one of them. X minus delta x by 2, and this is not fy, this is fx dx, so everybody's sleeping, and equals to something. And that's something we want to find. Basically, if we find is equals to 0, there is no whirlpools in there. If we find that it's different from 0, there are whirlpools in there. If it is positive, it's rotating counterclockwise, and if it is negative, it's rotating clockwise. So let's look at the first integral. The first integral is integrating from this point to this point, right? So we have delta x. This is oops. The flux fy dy. So this so put simply, this integral corresponds to this path, right? It's this path. And it's been evaluated in the middle. It's been evaluated at the black dot. Okay. The other integral, the next that I'm going to put here in square, this integral corresponds to this one. So this is going to be the round. This is going to be the square. Now, the next integral that comes here is, let me call it the some sort of rhombus, right? The rhombus, this goes from is equal, it comes to be this integral over here. Let me actually see if I can get this color. Let me see if I can get this color. Oops, it's a bit too thick. So this one is this one over here. And of course, the other one is the other one we find in there. Okay, so those integrals we have to do. And we're going to assume that the field is constant on each one of the points. Therefore, we simply multiply by delta y, because let's say it goes from delta y by 2 negative to delta y by 2. So the integral is simply delta y. So we will have the function evaluated in the middle. So the first one will be x plus delta x by 2, comma y, comma z, delta y. That is what the first integral is, right? The second integral will be minus f of x minus delta x by 2, y, z, and then I have those two integrals. Then I'm going to move it a little bit to the right. All right. Then I have plus, and this will be fy. This would be fy. So fx, now it changes. Fx from x, comma, y minus delta y by 2. That's the comma z. Then multiply delta x minus fx of x delta plus delta y by 2 z. Okay, so that is the integrals come out to be that. Then according to the formula that we just derived, we need to divide everything by delta area, which is going to be 1 by delta x delta y. So we need to do all this. And then we reorder this equation in this way. We're going to go 1 by delta x, and it's going to be fy from x plus delta x by 2 minus, no, here is this. This is the small thing here. Let me actually change this when I put it a square. Minus fy of x minus delta x by 2. All right. This one gives me the first term. So I am working with the first line. And then plus, now I work with the second line, f of x. I don't put the other sign, just put the ones that change. It's going to be y minus delta y by 2 minus fx y plus delta y by 2. And I'm going to move it right. And I'm going to divide this by delta y. Put it like this, right? And then make it like that. Can I make it smaller?
You're not joining the class? Yeah.
There is a question there.
I don't think that's Professor Leon. Okay.
I what? Say it again, please.
It was a mistake.
There is a mistake here?
No, I had an open mic, sorry.
Professor De Leon, I think is missing the second term of the upper equations multiplied by delta
Yes.
x, I think. Delta x and delta y.
Here is delta x, and here is delta, this is delta y. And this is delta x. Both of them are missing. Thank you for me. At least not everybody's sleeping. Okay, and now we take the limit when, for this case, delta x tends to 0 and delta y tends to 0. And as you can tell, it will immediately be the derivative. So all this equation, what it is d dx fy at x, y, and z. And it would be minus, because the positive is here. So minus d dy of fx of x and y and z. All right. And this will be the z component. And the z component means, in terms of here, that I have the plane, the direction of a plane is in the direction z as a vector. Let's call it as the directional vector of the area. The surfaces of the areas will have a direction, right? And normally they are, by convention, the direction of each one of these surfaces is coming out of the surface. So in here is easy because we have a cube and we know which one is the out direction. But it's not always easy to know which one is the out direction. So fortunately, we can leave the math to do the work and we will automatically get what is the out direction. But if you don't have if you have a simple plane, right, that's your plane. So you will have to take that the positive side is like this, right, coming out. And that is if this plane is the x, y, z plane. So this would be the x, and over here would be the y, is very clear. But if you have something like that, right? So how do you know which one is out, right? You will have to, somebody will have to give you which one is the z, if you give x, y, and z. So if z is this way, of course, the thing is coming out that way. If z is the other way, then it goes out this way. By convention, we know which way it will be. But when you're drawing things, it may not be that clear. Now, this is the first component of that tool. But there could be whirlpools in the other directions. There could be whirlpools here. There could be whirlpools here, right? So we have 3 directions, and when you put it all together, the easiest way will be, I am going to use nabla, even though I don't like it much, but it will be nabla of the vector f, and in particular, I'm going to put my vector is h, can be simply obtained by the determinant of this thing. But it's not because this is the way it is. This is because that's how the derivation gives you to be. So it's the other way around. So we have hx, hy, and hz. And you just compute the determinant. But this equation comes from here, right? So that's what it really means. What it really means is, let me actually put it below. Let me lower this. So the way it really is that the first component over here, we will put d dy of hz minus ddz of hy, and this is in the direction x. The one we have computed is the one here in the middle, is ddz hx minus ddx hz, and this is in the direction y. This is the one we computed here. Oh, no. It's the last one we computed here, in the direction z, minus ddx hy, this is plus, and my plus dy hx in the direction z. So this guy over here is this, right? When we take the limit. All right. So this is what it is, and this is how we compute it, right? It's easy to remember. It's easy to remember to compute it in in a determinate way. All right. Any questions to this point? Nothing.
Well, Professor, one comment. Usually, the definition of the curl, I have seen in some texts that the upper definition of the limit. Up. The first definition that you put of the curl.
First one.
The first one is
Okay.
what is it? That one. Usually, in some books, they specify that is the normal component of the curve. Yes. Means they put n in cross. No, it's a point product with a rod or
yeah. You can say here point n if you want, right?
Yeah.
Yeah, but for me, it's not about all formalities at this point. What I want is the understanding of this. But of course, you can go mathematically and do it better than this. Absolutely.
Yeah.
But my experience is this. This is already heavy mathematically. If you put even more heavy mathematics, the students will understand even less. That's my concern. But if you can have it with full formality and the students following you, very good for me. I wish I could do it, but I can't.
No, I understand.
Everybody gets lost. Everybody gets lost. Yeah. So I even don't know at this point how many of you are already lost. Yeah. I know you're not, for me, but I don't know the others. Fayaz, are you lost or you are okay?
I'm okay, brother. I'm okay.
Are you sure?
Yeah.
I am gonna take you. I'm gonna make you an oral examination when I come back. Huh?
Okay.
Okay. All right. So this is how we represent this, right? Now, so these tools. Oh, let me just go all the way. I think I already put this thing. This guy, I am gonna move it up because that's what it is called, the chord, right? That's the chord. And I put it in, it's too black. It should be black, but not that big. So this is the chord. The chord. And what it measures is how many weird poles you have. There is a little way to visualize these things. I mean, let's say that you change the speed. The way the electromagnetic books give it to you is they give the field like this, right? If you have a field like that is growing like this, and a field like this makes no sense. It's much better, or it's much realistic that you will have a field like that. Okay. Something like this is better than the other one because it just doesn't make sense to have the water speed near the edge to be larger than the water speed in the end. Now, if this is not near the edge, and this doesn't even exist, for example, and then you have some other things going on there that you don't care because in the end, you're going to come up to this point, right? That's the point that matters. We're going to shrink everything to that point. Then it's okay. Then it's fine. It's fine that you have this representation. Okay, so this page was reserved for the chord. Okay, we are very close to come up with the Maxwell equations and then how to interpret the Maxwell equations and what are the solutions? How is that solutions exist? So Stokes theorem. Stokes theorem is the actually, I want to derive the Stokes theorem. So this is the way to derive the Stokes theorem. You have a surface, and you want to know if in this path you have a curve, and you want to shrink this to a point. So you divide it into subsurfaces, right? We divided here into subsurfaces, all these things. It doesn't really matter the shape. So, and to each one of these, you assign a direction. Yeah. Normally, you will assign the traditional direction here, right, to this one. Let me actually even change colors. It will be much nicer if we change colors. Then you have this other one, and this other one rotates the same way. So it goes negative here, right? Negative with respect to the other one. And then we have another one here. And it goes that way, that way, that way, and that way. And we can have any number of things, right? Let's say the blue. Right. And this is the last one I'm going to draw. That way, that way, that way, and that way. Now, if you want to integrate over this surface, you will say, okay, what is the sum? Let me change on the color. This blue is not so good. The sum of all these surfaces, like from I equals 1 to n, of these little contours, they call it the CI, not there. Of this over each one of the little contours, it's a closed integral of F, whatever field of force is there, times the path. Let's call it dl, no, dc. Let me call it dl. dl, this is also vector, right? And that should be equals to, look at this, right? Everything cancels. When you do this sum, everything cancels except the thing that is at the end. Oop. Except the thing that is describing the bottom part, right? Let me put it this way, all internal things reduce, because when you are integrating this contour, the red contour, when you're integrating this red contour, okay, you add this amount of rotation if you wish. But when you go to the blue one, it negates this part. When you go to the orange, it negates this part. And the ones on top and whatever keep on negating all internal integrations. So at the very end, you end up only with the black. So then you say the integral, and I'm going to put it in black, the closed integral over the perimeter, right, of the perimeter of the surface, okay, of the perimeter of that surface on the force dot dl is equals to the sum of these things, right? Then the way I can do it is I divide all this by this surface, and then take the limit, and I'm going to put it a new equation. No, let me push it that way. And then finally, I take the limit when delta S tends to 0 of all this. Okay. Now, if you move this thing in, so you're going to have 1 by delta you still have the limit. Yeah, I'm gonna put the limit inside, right? I'm gonna leave this as a the sum outside. In fact, it's the sum what I want to get outside. The integrals and sum can commutate, no problem. They in the end, integrals and sums are the same, but I want to leave the sum at the end. The sum at the end from 1 to n limit when delta s tends to 0 of the closed integral of f dot dl, right? And this will be equal to the closed integral of the perimeter f dot dl. And I have 1 by, oh, I have to put it this way. Yeah, the limit I put it here. Everything here is in the limit. So now I have exactly the same sum to n, but I can see that here I have immediately, I have the definition of the curl. So it's curl of f, right? It's the sum of the curl of f. And I'm missing a multiplication for delta s. No, it's all right. Have the curl of s in here, and I have in here the same thing, the closed integral of the perimeter f dot dl. And I think that's it. That's what I want. I from a equals 1 to infinity. All right. And if I shrink it to a point for each one of them, I will get the same. The curl of f is equals to the integral, closed integral of f dot dl at a point. And this is exactly what I wanted. So, yes, I am missing the surface integral.
Surface integral.
What happens, correct my derivation for me.
Yeah, you need it's the integral of the rotational, no surface integral of the rotation. And I think it's missing where.
Let me see, where is missing here?
Is not the summation that becomes that?
No, I know where it is. I know where it is.
Mhm.
I divided here, but I need to multiply for it here too. Delta Si. So I am dividing here, right? This integral is okay, right? Then when I put the delta S here, I need to put it over here. Delta Si. All right. That is okay. Now it's fine. I think now it's going to be correct. Then I am still multiplying here by delta Si, delta Si. And I am still here multiplying by delta Si, delta Si. All right. Okay. So then I am going to put it in there here. See, I put all these things all together like that. Okay. So when I sum up this integral, so the sum of I equals 1 to n, the curl of f, and multiply for delta Si will be equals to the closed integral. Somehow, I think I shouldn't have multiplied the whole thing by that. Yes, it's not here. should only be here. Delta SI. Delta SI here. Delta SI here. And delta SI here. And that's it.
And divided by delta ESY.
Here,
It's missing one over delta S, like here.
In the second step.
And second there.
right here, right?
No, one above.
The limit of one, yeah, yes.
Yes. So let me move this guy a bit here. And here is 1 by delta SI.
Exactly.
Yeah. So when we take the limit is like this. And then this integration, this integrating over the whole thing is the surface integral of the curl of F, the S, and is equals to the to this equation. This is a Stokes theorem. So the surface integral, let me put it better here. The surface integral of a curl of a function, ds, will be the closed integral around the surface. And physically, what it really means is this, right? It means this, that all these little surfaces, all these little surface integrals that you will go here, all the internal paths cancel. And so if you're trying to measure how much a rotation or how many whirlpools are in there and in what direction, you should only integrate, can only integrate the around the perimeter. And that's it. You don't need to do more than that. Why is this very important? This is important because we have, let's say, Ampere's law in, let me put it here. The importance. The importance is because you normally have the closed integral of H dot dl equals to the area integral of J dA plus times derivative of the area integral of D dot dA. Okay, so this is very important because instead of this, and I want to change this to surface instead of area. Surface. Yeah, and this is surface. And this is important because now I can substitute this thing here. So instead of putting that thing in here, right, which this equation has full physical meaning. It's telling you very clearly that any current that you have, this is basically the current. Any current that you enclose by a path or by a line integral gives you some magnetic field. But now I can put this guy in here. I will have the surface integral of the curl of H ds will be equals to the surface integral of J dot ds plus the time derivative of the surface integral of D dot ds. So I can simply eliminate the surface integrals, and I come to derive that the curl of H is equals to J plus D dt D. And the value of this equation is that this equation is solvable. This equation in general, completely general, in general, this equation is not. This is not solvable. For a general equation, you can find examples, you can find cases where you could do this integral. But in general, it's very difficult. You can only do it for cylinders, cubes, or spheres. And some people go crazy and try to develop it for other things and get very sophisticated mathematical analysis and blah, blah, blah. But in the end, ends up not really working very well. Okay. So I had another one page here. And then this is a conclusion that I can come from the integral equation to this is the integral form. To the derivative form of Maxwell equations, here using Stokes in both of the ones in the above. And in these ones, I use the Gauss law. So then it becomes possible. I'm not saying easy. It becomes possible to solve these equations, and maybe the best way to do it is the best way. Let me change that. The technique that is more general and gives you better solutions for general problems is the final elements, and this is what we're going to solve. Now, all programs I know work on setting up the problem for different types of fields. It's not common that we solve the full problem as it is. The first thing we will do for anything that is related to power engineering, machinery, etc., is we just neglect this guy. This guy, it just doesn't exist. We know it happens in capacitors, and we know it happens in the transmission line. But for any local problem that you need to do, this component disappears. And we are going to disappear other components as we set up the cases in final elements. We are not going to go and solve the entire, let's say, electromagnetic field or the entire quasi-static electromagnetic field. We're going to reduce the problem to the minimum complexity that allows you to solve what you want. If you want to put everything, if you build a 3D model of certain size, it's just not going to converge in fast enough for being practical for engineering use. So we always do the minimum complexity possible that allows us to solve the problem. So now also there are some vector identities. So all of them can be easily demonstrated just by substitution of the components, right? I think I am going to work on these three. I'm going to need others. Maybe I need this one too. Maybe these four. maybe these 4 I will need to have a full understanding. The reason for this is because these things give the rise of use of potentials. And in most problems, in most electromagnetic problems, it's better to do, let me change that. In most of all electromagnetic 2D problems, so potentials are useful for 2D problems. They can be used for some 3D problems, but frequently programs will not, there is not much advantage. If it is a true 3D problem, say you have the current changing in 3 dimensions, then there is very little you can do with potential. But if things happen like in machines, let's say the windings of a transformer are in one direction, in the direction of the current goes in the direction of the winding, which follows the phi direction. So it goes through the angle. And if a conductor has only one dimension, so potentials will allow, as we will see later, maybe not even, not, I don't know today, maybe not today, to reduce the problem from the dimension of the problem. Why do we need to reduce the dimension of the problem? Is because not even the biggest computers today can really do a big transformer. We tried with the supercomputers we have to solve a 3D, big transformer 3D. It was like probably 200 or 300 MVA transformer. It had a funny construction, and we tried to put it, and we waited for months for the simulation to come out, and we gave up. So a full 3D problem is still not a practical. It's you can solve it, yes, you can, if you have patience enough patience. Is it practical? Can you use it for the design of things? Probably not. All right. So vector identities are important. Let me just validate the ones that is more important to me. The one that is more difficult to understand is the last one. The others are easier, but this one is easy. And let's do it. Let's develop it fully. So 16 is going, this is the divergence. This is the curl. And what this is telling you is the divergence of the curl of any vector is always equals to 0. Is it true? So let's put the divergence and let's write the curl of a vector. The curl we have just, let me see if I can steal it. Hopefully I can. Where is it? Where is it? Where is it? Here. Hopefully I can steal it from here. Oh, no. Like this, copy. And I'm gonna paste it here. Paste. Can I reduce it? No, I cannot. All right, I leave it like this. So I am going to compute the divergence of this curl. I don't know why I can't reduce it, but it's okay. Let me see if I can put this guy below. There you go. So, and it says that this is equals to 0. So, which means this will really have to be equal to 0, right? So when you take this is the gradient. This is the gradient, right? And this thing, this is the curl. So the gradient, what it means is the component x, which is the first component, is going to tell you. The gradient is you take
Sorry,
the,
Professor, it's divergence. No?
sorry, this is the divergence. Oh. The divergence of the curve, correct. So the divergence, as we saw before, is the divergence of a vector f will be d dx of fx plus d dy of fy plus d dz of fz. So it takes you from a vector to a scalar. Just like the curve takes you from a vector to a vector. Okay, so all right. So we are going to expand this for each one of these elements. So I'm going to have d second, dx dy, hc, minus d second, dx dz of hy, plus, for this, it will have d dy, second, dz of hx minus d dx dy dx dy dx of hc plus d second dx dz, well, let me change it, dz dx hy minus dz dy of hx. Is this equals to 0? Well, let's see. So over here, I have this one should eliminate with one of them. So I am looking for dx, dy, and hz. So which is here, right? This one eliminates with this one. This is positive here, that is negative there. Now, let's say the second term. This term eliminates, let me say this eliminates with a and with minus a. So this is b, eliminates with this one. This is negative here, this is positive here, so b eliminates with b, and therefore the other one will eliminate with c. So 0 is identically 0. So this is true. The divergence of the curl is equals to 0. And the same you can do for all others. Yeah, the same you can do for all others. These were already derived, and you can do the same for with all of them, right? But that one and this one, these two are extremely, extremely important for the potentials. The potentials is the way it solves things. Okay, this is very important to when you are deriving the typical way it's reversed. The way we normally write this particular thing is, let me not go, oops. Why is it that, oh, something went wrong here. Let me close this. It doesn't let me erase. It doesn't let me erase. So let me go undo, 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 undo. And not even that. Okay, I like to say that this equation is better written like the curl of A equals to the gradient of the divergence of A minus the Laplacian of A. This is a better way to write this equation. This is a way that we're going to use it more. All right. Okay. And that thing is going to stay there because I don't think I can. It's annotating in a different program. It's annotating from Zoom. So clear all drawings. All right. I was able to do it. Okay, so now there is one more function. So the gradient here, let me just derive the gradient. The gradient, which applies to a scalar. The gradient takes you from a scalar to a vector. And this vector is gradient of f is d dx of f in the direction of x plus d dy in the direction of y plus d dz in the direction of c. And the gradient has all sorts of physical interpretations. Perhaps the most important one is if you have a function, the gradient is the slope of the function at a given point. So that's what the gradient will give you. This is the gradient of that function at this point. Because it is coming from a derivative, and we know that the derivative is a tangent at a point. So, and it's used to minimize things, the gradient, and it's used for things. But in magnetic fields or electromagnetic fields, the way we use it is this way, right? Is to help us solving things. Okay. There are two ways in which we solve problems. We solve electromagnetic problems. We solve the solution of EMF problems can be done by fields or using potentials. If you can, you will use a potential. And frequently we can. Most practical problems can be solved using a potential. But if not, then we have to go to magnetic fields. And I am going to illustrate all this starting with the electrostatics. Electrostatics is the easiest way to start. Electrostatics comes from the curl of H equals to J plus time derivative with respect of D, and then the curl of E equals to minus d dTV, and the divergence of B equals to 0, and the divergence of D equals to the current density, right? Something like that, the charge density, volumetric charge density. And we never forget about J equals to sigma E, and D equals to epsilon E, and V equals to mu H. Okay, but in electrostatics, the name says statics. So there is no variation on time. There is no variation of time. So Electrostatics would actually even eliminate this, right? There is no magnetic field because this current, even though you don't see a derivative there, in the end, this is current, and it means that is charges divided with time, right? You can say it's d, dq, dt. So something is moving there. Fortunately, we don't even need it. We don't need this thing. But so the two equations that we need is the curl of E is equals to 0, and the divergence of D equals to rho V plus this guy, which tells you that D is equals to epsilon E. Now we're gonna play with this thing a little bit. And the first thing that we're gonna do is to put this guy in there. So we will have the divergence of E equals to rho V by E. I am assuming that the medium is nice and is beautiful. I have to put this dot here. I am saying that the field is beautiful, right? It's the medium is beautiful. So this means it's linear. Therefore, I can get it out of the derivative. Can I get it out of the derivative always? In most cases, the permittivity is constant by material. It's not constant at the boundary conditions between different materials. And it will be rare that you find a material that has, for example, the properties that change with direction, that change with magnitude, non-linearities. So linear, isotropic, and homogeneous. And I would say I have never come to something that is not like this. Maybe if you want to analyze corona effect on a transmission line, you may have to do some crazy things, but that even will go beyond this. It will go beyond fields. So I have not come across a problem in which I cannot do this. All right. So how are we going to solve it? How are we going to solve it? The way we solve this is we put the curl here. And then I'm going to take it over here down. The curl of E equals to 0. But then I go back here and use this equation, right? So it's going to be that this is the gradient of the divergence of E minus the Laplacian of E equals to 0. Okay. So I am going to put this guy in here, right? And I'm going to get that this equation develops into the negative of the Laplacian of E is equals to, well, the negative, it goes with the negative, is go with the divergence. No, let me see. Yeah. Put this guy here, rho V by epsilon. So it's going to be equals to the gradient of rho V by epsilon. Right? That's the equation. That's the equation that we can solve. This even has a name. This is Poisson equation. Now, if you don't have an insulator in which you have a this epsilon is too ugly. There are regions where you don't have a charge. If you have a charge, this is what you need to do. But if there are no charges in that region, no volumetric distributions of charges, this equation reduces to the Laplacian of E equals to 0. And this is Laplace equation. Both of those equations can be solved. Yeah. So in many cases, let me develop this equation. If I develop this equation, will be the Laplacian of AX in direction X. Remember, this gives you a vector, right? This is all a vector, plus the Laplacian of EY AY plus the Laplacian of EZ AZ, and this will be equals to 0. So you have here three different equations. By this being equals to 0, I mean the vector 0, 0, 0. Therefore, is really three scalar equations, Ex equals to 0, the Laplacian of Eqy equals to 0, and the Laplacian of Ez equals to 0. So it's three equations. That's what we really need to solve for a true 3D problem if you solve this by fields. Is this easy to solve? It's relatively easy to solve it, even if you want to do analytically. If you have, let's say, one independent variable, so let's say that you have only one field. You're talking about parallel plates capacitor, right? So this is plus, minus, and you have different permeabilities, permittivity 1, permittivity 2, permittivity 3, and you can solve it, and the field goes only one way. Maybe it changes, is the example that we saw before. Maybe it changes with the location. You only need to solve this. No need to do anything else because you will go that way. And it's only one direction. You may even have that this even becomes, for a case like this, is the second derivative with respect to x, assuming that this will be x. Everything is symmetric. Of if x, which is a function of x, and is equals to 0. And you can solve this. Of course, the excitation needs to be included somewhere because you're going to put the negative here, you're going to here, put it here, and you're going to get a boundary problem, right? The boundaries will give you the excitation, but there is no impressed charge in there. Okay, but let's see what there are analytical solutions. I will not discuss analytical solutions. There are some very nice analytical solutions in 2D, in 3D, maybe beautiful analytical solutions that take hours to derive, and in the end, well, they are good. But if I do something crazy to that capacitor, say I want to see what are the imperfections of the parallel plates, then this problem is not solvable anymore. There is no analytical solution for such a thing. And if you put it in finite elements, it takes you just a little drawing to do it. So I will not discuss analytical solution, not because they don't have value. In fact, they will have a lot of value because if you solve this problem, analytically, and then you solve this problem with finite elements, and the results give you too much of a difference, you are wrong. Most probably in the finite elements, because the analytical solution is easy. So using analytical solutions to validate your finite element solutions is a very good idea. So first use your finite elements to solve this. And if it matches well with the analytical solution, then you go and solve this. If not, I wouldn't believe your final element solutions. I would probably think that you have a problem. And because programs are relatively, I would say, easy to use, but they still have a learning curve. You cannot just get a final element program today and start running cases today unless somebody tells you step by step. It's they have a learning curve. Sometimes the actual deep details would actually take years to get of constantly using it. If you have real problems to solve, you will see that the mesh is very important, the boundary conditions are very important, and the space that you model is very important. And if you want an efficient and accurate solution, you need to do it one way, another way. The way the elements are decided, which kind of elements. If you want triangles are the favorite because they fit most curves, but they are not the most efficient. There are other ways. If you are able to kind of guess the field and put the meshing in a way that the field is, let's say, the equipotentials are part of your meshing, you are getting a lot more efficient and more accurate results. We will talk about all these things when we get to finite elements, which is not too far. The other thing, the next thing I want to see is the solution of the same problem by potentials. So I have the same problem. The curl of E equals to 0. The divergence to D equals to rho V, and D equals to epsilon E. I have the same problem that I wanted to solve. Yes, and but I know. Well, let me take the derivative of. Let me get one of these things. The one that I want is this one. Let me see if I can simply steal it from here. Probably I can do this. Where do you go? Oh, I see. So capture. So I can come and capture 15 like this. And go this way. Copy. And I'm going to paste here. Reduce it. Okay. I have this equation that I am putting on purpose next to that one. So these two look the same, right? I mean, I have the curl of E and I have the curl of a gradient, and they are both equals to 0. So somebody can tell me, well, maybe I can substitute, or I can say that E is equal to the gradient of F. If I do that, I will, if this electric field comes from the gradient of a scalar function, then I am doing no is equal to the gradient of a scalar function. So if I happen to be able to find that scalar function, then I solve the problem. Now, what we do typically is we do that, but we prefer to use the negative sign because this F, what we're going to do with this F is that we're going to say this is B, the voltage. This is the voltage or potential or any way you want to call it. So this is the voltage. So, and to give the right physical meaning that the electric field measures the force of moving a charge from the infinity to a point, to give that meaning to the electric field, which is the meaning that we want, it's best if we put that negative. Now, solution by potentials. Although there is physical meaning, so I want to make clear. So, although there is physical meaning to some potentials, the true power of potential, the true power of potentials is the reduction of problem dimensions. And we will see that in here. So let's substitute. We know this is true, so I can say that E may come from a potential, and then I am going to substitute this guy here, right? So I am going to have the let me put this here. Then this is E vector. This is D vector. Will be minus epsilon the gradient of B. So I substitute that in here, and it's going to get me E is equals the negative of the gradient of B, and it's equal to rho V, right? Again, I assume this is constant, so nice and beautiful medium. So I get it out, then I get epsilon out, and it's going to give me the gradient. No, this is the divergence, right? Here, the divergence. The divergence of the gradient of B will be equals to the negative or rho V by epsilon, right? And this guy, if you go up, this is called the Laplacian, right? So it will go, Laplacian of V equals to minus rho V epsilon. And this equation, you will find as is in, let's say, console. COMSOL. I don't know if ANSYS has it. COMSOL uses this equation, or a little bit more complicated one in which this value is not taken out, right? So it will give you the, I don't know, we're going to extract the Fayas, right? From an electrostatic field, we're going to extract what this one does. Because you need to take the derivative of minus derivative of epsilon. It's the first, okay, let me do it like this. It's minus epsilon by the Laplacian of B minus the divergence of E that multiplies the gradient of B. This is the equation that you will find in COMSOL. They will give you this equation for a general problem. I hope it's there. But the one that I like to go better is this one. Yeah. So this part is when the material properties change. This is for when the materials change. When the properties of the material change. And they have to change with the direction, right? So, okay, but now let's look at what has happened. What has happened is that this equation that I'm going to steal from here, let me say this one. This equation, copy, and paste here. This equation has become, okay, so you have these three equations. And by the use of potentials, I only need to solve the Laplacian of V equals to minus rho V epsilon, and then take the derivative or get the gradient of B. So this is a 3D equation. This is a 1D equation plus a derivative. Derivatives, we have no problem taking. So it's a 1D equation plus the derivative. And the derivative can have 3 dimensions. We don't care. So, but if you have a 3D problem, a true 3D problem, I don't know why this is happening there, but leave it there. So if you have a true 3D problem, electrostatic, it is much better to solve one differential equation than 3 differential equations, and then just take the derivative. Taking derivatives, it's extremely easy. Even in 3 dimensions, you have contiguous points. So you have these points, these points, these points. I cannot illustrate it in 3D, but you have these points that you get from the final element solutions. And then if you want to compute the derivative, well, just subtract one minus the other, right? The f of x, y, I'm going to do it into the f of x plus delta x, y plus delta y, minus f of x, y, divided by the derivative, maybe that's delta x, and so forth. I mean, it's just apply the difference between the difference equation between the points. In any case, final elements, the only thing it does is interpolating in between. So what I'm saying, this is not right, but what I'm saying is very easy to take a derivative. It's very easy to take a derivative. This is easy. Easy. Especially if you take it by computers and the points are already there. What in the end happens is that you just formulate the problem like this, and the computer will give you this problem much faster than if in the end, what you want is to solve this thing, right? What you want from here is to compute E. The same here, you want to compute E. And the computer will give you the solution of both ways, except that it will be 1/3 of the effort on the right, and on the left is going to be 3 times as much. So that is the power of potentials that we have to, or we can simply use one dimension, even when the problem is 3 dimension. Any question to this point? Is there somebody still awake?
No question.
No, nobody is awake? Okay.
No questions.
All right. So the same way that we have done electrostatics, programs will come and do magnetostatics. So there will be 3 ways. So several ways. Electrostatics is what we have done, and you will have the Laplacian of B equals to something, right? It could be equals to 0, to a positive number, to a negative number of 0. Oh, let me change it like this. It will be equals this to this to this. And that's what you do in electrostatic. Magnetostatics, it's another thing that we're going to see in a moment. I hope I can see them all. Then we will have DC current, and then we will have AC current. And for completion, you will have full or complete EMF. Complete EMF. Okay. Each one of them has a different way. In magnetostatics, for example, magnetostatics will go and tell you that you have a so let me do it independently. So these are the ways in which the programs are divided. Fayaz, is there a facility in Console to do magnetostatics only, or you need to do AC/DC?
Sir, in the AC/DC module, there is a option of like
In the AC/DC module, you can pick magnetostatics.
yes.
All right. Okay. Then magnetostatics will be the same thing, right?
Yeah, it's stationary. It is doing magnetostatics.
So magnetostatics will give you the curl of H is equal to 0. There is no current. It will give you the divergence of B equals to 0. And it will give you that B is equals to mu H. And again, you can have I call this the voltage, but the actual name of this potential, it will be the electric scalar potential. It is the voltage, don't take me wrong. It is the voltage, it's the common voltage that we use for everything to solve circuits, that's what it is. But here we're going to call it the electric scalar potential. So if you see these equations, which are the equations of magnetostatics, you can go and solve them in different ways. And the way that you can go directly for fields, right? You take here the curl of H, because you take the curl, right? You take the curl equals to 0, and no blah, 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 blah. You can go that way, right? But you can also define, so let me go this way. So the curl of H is equals to 0 by taking the curl of this equation, right? You can also, there is another possibility, is, let me not confuse. Let's go one at a time. Magnetostatics first, and then we do the other ones. So magnetostatics, you have the curl of the curl of H equals to 0. Following the expressions that we have done before, so let me, where is it? No, in fact, I don't even need to do this. I don't want to do this. This is actually more complex of what I wanted. I can say that I invent a potential, even negative, and it will equals to 0. H can be coming from a vector called, for a scalar called F, and F is the scalar magnetic potential. It is not commonly used. It's something that you can only use it for magnetostatics when you have that J is equals to 0. If J is equals to 0, you can use it, and it will give you exactly the same properties that here. It will reduce a 3D case to a 2D case. So F, this potential will reduce a 3D or 2D case to a 1D problem, or 1D case. So exactly the same thing. So you can solve this case by fields, or you can solve this case by scalar magnetic potential. Assumes that there is no current. So if you happen to have a problem like this, you can simply use the scalar magnetic potential. The more typical one is not electrostatics, but it is the DC current. DC current, which DC current will give you the curl of H equals to J, the curl of E equals to 0, the divergence of B equals to 0, and I don't gonna need, I even not even going to need this guy, but I put it there because, well, it's there. And I am gonna have the B is equal to mu H. So with these equations, and using another one of the vector identities, let me go all the way to here. So I am going to use this other identity. I'm going to use 16. So I use 16, scroll all the way down, paste. So I look at this equation. So this tells me that I can define B as coming from the curl of a vector A. And this vector A is the magnetic vector potential. Okay, and it gives me not exactly the same power that the scalar vector potentials give me, that the scalar potentials give me, either electric or magnetic. But they still give me, it still gives me a lot of power. Why is it that I can substitute this here? Because if B is coming, let's say that B is coming from that, so the curl of A is equals to 0, so which means B is equals to the curl of A. If that happens, it's true, then it's fine. So, but what I'm going to do is I'm going to work upwards, and then I'm going to say H will be 1 mu V, or 1 by mu, the curl of A. And then I am going to put this guy in here and follow the arrow, and it will get me the curl of 1 by mu. The curl of A will be equals to J. Assuming that things are all nice and beautiful, then I have the curl of A equals to mu J. And the curl of A, using another identity, is the divergence, the gradient of the divergence of A minus the Laplacian of A equals to mu J. And we have already used that identity that I'm using here. Is the curl of curl, is the one that I put separated. I have separated it here. Yeah. Not that one. This one over here. Yeah, the curl of curl. Okay. Now, there is sometimes a little thing that is been done. Normally, we would say that the divergence of A is equals to 0. So we would say this one is equals to 0. And there is a way to make sure that it's equals to 0, the divergence of A. I don't remember the exact steps, and I will show that next time. But this is what we're going to do, and this is called the gauge, Coulomb gauge. I don't remember how to derive it exactly, but we can derive it, and becomes a true thing. So what happens there is that you get the Laplacian of A is equals to minus mu J. Okay, so this is a vector. So what is the power of this equation? So if I were to derive this equation, it expanded, will give me the Laplacian of AX equals to negative mu J, the Laplacian of AY, JX minus mu JY, and the Laplacian of AZ equals to minus mu GAZ. And it seems like I'm doing nothing, because if I were to solve the problem directly for fields, I will get the same thing. So if I go for fields or by fields, if I go by fields, this is by potentials. If I go by field, I will get the same. The Laplacian of, let's say, Hx equals to, it would simply be J, equals to the positive Jx, the Laplacian of Hy equals to Jy, and the Laplacian of Hc equals to Jz. So it seems to be the same. But the difference is that in general, most of our problems are in a way that they are, let's say, a conductor is like that. A winding will go like that, like that, like that. So here the current is in one direction, let's say IZ. Here the current is in one direction, I phi. So we're taking advantage from the fact that A and J are collinear. Okay. So, and in general, J is 1 or 2. Let's say is, 1. Let me change that. J has 1 or 2 dimensions. So, an H can have more dimensions, can have 3 dimensions. Say, this problem that I have here, I have a conductor. But now it's not an infinite conductor, it's a real conductor. If you're going to compute the fields in the middle, it will be perfectly like that. But if you're going to start computing the fields close to the edges, it's not going to be like that. And of course, this is not completely realistic, because the current will not be completely close, but you will have 3 dimensions for the field. If you have the current like this, you end up having 3 dimensions for the field, or at least two, because it starts deforming, right? It's going to go bigger and bigger. It's going to have deformation. It's going to have something like that. And it may actually even come and close on the other way. So even for this, now, if you have a winding like this, in which you're moving the current in this dimension, the magnetic field is going to be vertically in the middle, but it's going to come like that, and it's going to come like that, and it's going to come like that, and it's going to come like that. Yeah, and then this is basically a 3D case. Not exactly, because the phi is the same, but at least if you have the current in 1D, in the phi, you will have the field in 2D. And if you say, no, I have to XY, so the current is in XY, and the field is in XYZ. So even under those conditions, it will be much better to solve it by potentials. It will reduce at least 1 dimension your problem. And reduce 1 dimension is basically delete one of the equations here. So 1 or 2. If you do a reduction for 2, like something that is linear, I'm saying one dimension, you have only one. Okay. I think I'm going to stop there. I am going to have homework for me. Remember this Coulomb gauge. I don't remember at this point how to do it, and I don't want to start working math and I'm failing. I will eventually get it, but I need to remember it. So let me stop share and see if I can see anybody. I don't see anybody. I'm going to show my face. So,
Yes, Professor.
yeah, speak a bit louder or let me increase the volume here.
Professor, like the thing which you asked is that when the current is zero, curl of H is equal to zero. When J goes to zero, is used for permanent magnets when current is not there. And there is a separate.
No. It could be that there is no current in the region that you are studying, but it's not necessarily permanent magnets.
Yeah.
Okay. It's just the point at what you're looking at, it has no excitation. Permanent, you are looking at the macro problem, and this is no macro. This is point by point. So what it means is that at a given point, there is no current.
Like the things which we are doing in which the J is there. Like if I see into the console, in the equation section, the curl of H is equal to J is mentioned. But there
Yes,
is another option where magnetostatics with no current.
correct.
And that is used for only.
And that will
magnets.
apply to magnetostatic only permanent magnets. I agree with you on the entire universe. But if you have to solve
Professor Chatir,
okay,
can you see the screen?
I can see your screen, but I think we're going to show. Oh yes, that's what I wanted to show. Very good.
Yeah. So like for the magnetic field, the stationary study, the curl of H is equal to J, right? The thing which we study.
Yeah.
And here there is a different equation that J is equal to conductivity E plus conductivity V times B plus J. Don't know what's there. And there is in the electrostatics, these are the equations like Gauss's law and E is equal to minus del V. Now the Poisson's equation. And then in magnetic fields, no current. That's the equation, and the magnetic scalar potential which we discussed the last meeting. The H is equal to minus del Vm.
Okay.
Yeah.
Well, that's good. Those are the equations.
Yeah.
Let me see the electrostatics.
Electrostatics.
Yeah. So those are the equations. It's completely general. It's not going to use epsilon for constant for any reason. Yeah. So those are the equations that can be solved. Okay. Very good, Fayaz.
And then there is another option, no currents boundary elements. So these are two separate studies, like options. No currents for permanent magnets. And I have not used these two, but I don't know.
Okay. No, this is very good to know. I don't know how to use this program, and I mean, I don't know if I've been fortunate or unfortunate to always have students doing it for me, but I've never learned to use the programs. So I'm not about to start learning. I have other things to do. So
my question is that what is that equation? J is equal to conductivity E.
That it needs to come from the Paradise law, right? JE has to be the impressed current. That one is the speed. It's speed times V. So it's a voltage moving. It's a magnetic field moving. So and the other is the magnetic field, in the induced magnetic field. Now, JE is impressed. I'm pretty sure that is the impressed current. That is a current that you put. Okay.
Okay.
Now sigma E, that is the current that,
Ohm's law. Conductivity.
yes, for Ohm's law. And that one comes from the induction. Yeah.
Like that's that
It's the
conductivity.
conductivity and the speed. So it's the time derivative, if you wish, the time derivative of V. It comes from Faraday's law.
I think it's a conductor moving in a magnetic field, right?
Correct. Correct.
Conductor is stationary. Magnetic field is moving.
Conduction is stationary, magnetic field is moving. It's the same thing.
Yeah.
It's the same thing to have magnetic field moving or electric or the conductor moving in a magnetic field.
Yes.
The only thing that is important is that it changes with time. In that way, there is induced voltage, and then if there is conductivity, there is induced current. Those are the eddy currents, if you wish. Okay. So you have, in that equation, you will have impressed currents, you have currents, DC currents, and AC currents. You put it back.
Okay. This one.
So the way I like to see this is the left is DC currents. You have J equals to sigma E. That's a DC current. Plus sigma speed times V. That is an AC current, right? And JE is impressed current that has nothing to do with the magnetic field. It's just you invented it there, right? You impress it there one way that is external to this problem.
Thank you, Professor.
All right. So very good. I'll see you in person to the NYU people next Tuesday. And I still see you virtually to the Mexico people. Right now I'm in Cancun, so it's I'm in Mexico, but still very far. Yeah.
See you, Dr. Leon.
All right. Take care,
Thank you.
guys. All right.
Take care. Bye.
Bye-bye.
Thank you.
Bye.